Hello, in this video lecture, I'll be solving some op-amp numerical problems and which might help you in completing the latest homework. So let me begin with some golden rules on op-amp. So this is the op-amp. So op-amp has input impedance, output impedance, and this is the voltage source, which depends on the input voltage. But for most of the cases you just need a triangular shaped symbol with just three terminal, inverting input, non-inverting input, and the output, right? And like I said before, if you want to make a op amp as a stable amplifier, you need a negative feedback to the inverting input. And then these are the golden rules. So any ideal op amp has very high input impedance. This Ri input impedance is very high, actually tens of mega ohms. So that's why we can assume that the input draws no current. So the input current here is almost zero. And V plus, this is the most important rule for op amp. V plus and V minus are always equal to zero. Why? Because since op amp has very high gain, voltage gain, so if you have a slight difference in this differential voltage, then the output voltage will saturate, so that's why if you want to work and make op amp as a stable amplifier, this must be equal. So they are forced to be equal. And then to solve the circuit problem, then you just apply the same in a KVL, KCL nodal analysis for each node, and then use this condition to solve the problem. Alright, so let me begin with a simple problem, and this is about inverting amplifier. Okay, so here's the question. So the following circuit is configured as an inverting input, inverting amplifier, and then it's just asking for this configuration. It's just asking what would be the output voltage. So first, your power supply voltage is plus minus 12 volts. Usually you don't need to show that. Usually we don't show the power supply voltage, but you may want to put here. So because to operate an op amp, you need the power supply, both positive and negative polarity voltages with respect to ground. Okay, so first, if you're applying plus and minus 12 volt to the op amp and resistance values are given, this is 10k kilo ohm, this is 1 kilo ohm, what would be the output voltage, right? So you apply V input voltage as 1 volt peak to peak, right? So your input is peak to peak 1 volt. So what would be the output? So that's the question. And then you just use the regular idea, in op amp you know that V plus is equal to V minus, right? And has to be equal to 0. Because why? Because this is connected to ground. Right? V plus is grounded. So that will make that will automatically put the V minus at virtual ground. So that's the condition. Then we apply KCL, Kirchhoff's current law, at the node V negative right here, and that means you have I2 plus I1, just two currents, is equal to 0, and then use the laws, voltage laws, Ohm's law. So I2 is V initial input minus V negative divided by R2 plus V out negative divided by R1 is equal to 0, but V negative is at virtual ground, so it's 0 from this condition. And then you solve for V out. So V in over R2, so V out is negative R1 over R2 times V in. And then since we know the values, R1 is at 10 kilo ohms, both are in kilo ohms, so 1 kilo ohm times V input is 1 volt peak to peak, so it's going to be negative 10 volts peak to peak. So that's going to be the answer. Okay, so your output will look something like that. I'm sorry, this will be inverting, you know. So if you want to draw the output sketch, it will be like this, something like that. So this peak to peak will be 10 volt. Negative simply means the input and output are, you know, 180 degree out of phase. Now next question is, it has second part. Now the next question is, what happened for the same configuration, same resistor, same input, if the power supply, if you apply power supply as plus and minus 8 volts, what would be the output voltage look like? You know, so that's something you can just imagine. Since in this particular example, right, your voltage gain is negative 10. We found it from here, right? Yeah, this is the voltage gain 10 times. But output will look something like it, because output can't be greater than V out. This is important. Is always you know, less than or equal to plus minus VCC. It can't be greater than power supply voltage, right? So your it will try to swing, but it will saturate. This will cut off at plus and minus 8 volts. So your output will, this will be cut off. So this is positive 8 volts, this is negative 8 volts. So if you check on the scope, it will look something like that. It will be like a clipper circuit, okay, because the output can't be greater than you know, power supply voltage. Since power supply voltage you are applying here at 8 volts peak to peak, so it can't go beyond that. Okay, it will be clipped at plus and minus 8 volts. Alright, so that's what you need to know. So next is, I'm gonna now try to solve this problem. So this circuit looks a little complex, you know, complicated, but it's not actually complicated circuit. So you can easily divide this whole circuit into two parts. So two parts is like this. First part is just the amplifier, like this. Before you apply input to the second op amp, first you need to figure out this voltage output, let's say VO1, right? And this is the first stage of this op amp, is just the inverting input. This is, you know, the resistance in terms of V1. You can right away you can find the VO1, and after that you're applying two voltages here, this and this voltages to the inverting. So then you can apply KCL, and if you remember from the theory part, this second part is just the adder. This is just the adder, and you can actually, you don't need to memorize the formula, you can just derive it by using KCL. First stage is just the amp, inverting amplifier, and second stage is just the adder. So first our job is to find VO1 in terms of V1, right? And we know this is inverting input, and if you remember from previous problem, so VO1 for inverting input, inverting amplifier is negative, here in this case 20k, this resistance divided by that resistance, right? Or you can just do KCL here if you don't remember the formula, times V1. So that's negative 2 V1. Let's call equation number 1, because we're gonna need that for here. Now for the second amp, second op amp, so apply KCL at V minus. So I'm gonna apply KCL right here, right? So then it's going to be three things coming in: VO1 minus V negative divided by 10k, right, plus V2 minus V negative divided by 10k, plus V out, very final output, minus V negative divided by 20k is equal to 0. The sum of all the currents is equal to 0. But again, since V plus is grounded, right, this V plus is grounded, that will force V minus also equal to 0. So these are all 0 then. 0, 0, 0. And then you can find out, then you can solve for solve for the V out from here. So V out over 20k, right, is equal to negative the whole thing V01 over 10k plus V2 over 10k, and then you just put the then cross multiplication. So it's V01 is from equation number 1. V01 is negative 2 V1, negative 2 V1, and so 20k divided by 10k plus V2, which is, just keep it as V2, 20k over 10k. Okay, that's going to be your final answer. That's it. So if you want to simplify, negative, so this is negative 4 V1 plus 2 V2. Alright, and then so V out is equal to 4 V1 minus 2 V2 is your answer. That's your very final answer. Okay, so that's how you solve. So though it looks little complex circuit, it's not actually complex circuit. You have to separate into two stages and then solve it as usual. Alright, so now I'm gonna solve next problem, something like that. Okay, so op amp is connected as shown in the figure. Op amp is configured with the inductor in the circuit, and it's just asking what's the output expression for the output voltage here, output in terms of the given variables. Okay, so then again here V plus is connected to ground, so that means that will force V minus to be at virtual ground. So that's the condition, right? And V plus is equal to V minus is 0 volt. So that's from the given configuration. And then we're going to apply, remember this is also called virtual ground. Right, this word is the popular word, virtual ground, because even if it is not connected to ground directly, it will force to be 0 volt, at 0 volt. That's why it is called ground, virtual ground. Okay, so we're going to apply KCL at V negative, right? So IR plus I of L, you can use small letter I or capital letter I, no problem. So IR is negative IL, but remember IL is 1 over L, if you remember, some initial time to final time, the voltage across the inductor integration. That's IL. That's the formula for IL. IL, which is the inductor current, is 1 over L integration of the voltage across the, but this is 0, this is at virtual ground, so IR is negative 1 over L, some T0 to T V out dt. Let's call equation number 1 because we're going to need it later. Okay, but here IR from this configuration, IR is just this voltage minus that voltage divided by R. So input voltage minus V negative divided by R is negative 1 over L integration of V output, and this is 0 again. So V input divided by R is negative 1 over L, T0 to T V naught dt. and a couple more steps. So V input is negative R over L, and then taking derivative both side, time derivative both side, to get rid of this integration. So that's going to give you the V naught, right? So then that's it. So your output is negative L over R factor dVi over dt. So that's simply a differentiator. It's called differentiator, okay, because the output voltage is proportional to input differentiation, derivative of the input voltage. Okay, since you can clearly see, right, the output is some factor, negative simply means inverting, some factor, and the derivative of the input signal. So this is simply, it's nothing, it's just a differentiator. If you want to differentiate the input signal, then you connect the circuit like that. See, you can see op amp can do a lot of functions, mathematical functions as well. Okay, let's move on. So next problem is calculating the bandwidth from the given voltage gain data, which this will also help you in completing the lab number 7, because at some point you'll have to calculate the bandwidth product. So in this diagram, it says find the gain bandwidth product, right? It just say gain times bandwidth product, right? So we're gonna take just a couple examples. So starting with gain 10. So how would you find the bandwidth? So bandwidth is something where the initial gain has dropped to 70%. So FC, right, it is 0.7 times 10. So it's somewhere here, right? So then gain bandwidth product is 10 times bandwidth here, right, which is, you have to figure out this curve where the initial gain drops to 70% of the initial gain is about 100k, is 1000k. So gain bandwidth product is about 1000 kilohertz, which is 1 megahertz. That's it. So let's take one more example, because gain and bandwidth product must be same. So now we're going to take, I'm going to take gain 100. So let's check for gain 100. So if FC is somewhere here, so you lose the gain bandwidth. You can clearly see, right, if you increase the gain of op amp, you'll lose the bandwidth. So your bandwidth is for 100 gain 100, your bandwidth is about 10 kilo. So gain times bandwidth product is 100 times 10 kilohertz. These are hertz, kilohertz. It is about 1000 kilohertz, which is constant, just 1 megahertz, right? And you can clearly see this fairly remains constant. All right. So next, let's move on. Let's do a couple more problems. So the next is for the given configuration, for the given circuit. So these are the registers, register symbols are same. So this or this, some book use this, some book use that. This is the standard, but some book also use this. Okay, for the given configuration, if V1 is, so V1 is 1 volt, V2 is half volt, what would be the output? Okay. So V1 here input 1 volt, V2 input is 0.5 volt. What would be the output voltage based on the resistance? So here we're just going to apply again same concept, the KCL, KVL, whatever possible. So first we have to figure out what is V plus, right? So you can clearly see V plus is just the voltage division across 10 kilo ohm. It's just the voltage across. It's the voltage across 10 kilo ohm, right? Which is from voltage divider. you can just use voltage divider circuit then, right? Which is we're looking voltage across the 10 kilo ohm, 10 kilo, so keep everything kilo ohms. So this is also 10, right? 10 plus 10 kilo ohms times V1 is the total voltage. So this is just 1/2 of V1, which is 1/2 of 1 volt, right? This is 0.5 volts, V plus. Okay, we're gonna need that later. So V plus is at 1/2 a volt. Now we're gonna apply KCL at V negative right here. Okay, so then you have V2 minus V negative divided by 5 kilo ohm plus V out minus V negative by 10 kilo ohm, 0, and then you solve for V out. That's it. So V2 is at 0.5 volts minus V negative is, remember, V plus is equal to V negative, right, from op amp condition. So we're going to use this here. So that seems like 0. Yep, 0.5, 0.55k, this becomes 0 plus V out, we're solving for 0.5 divided by 10k is equal, so this is 0, they will cancel out, so V out is then 1/2 a volt. So output voltage will be 1/2 volt if you do calculation. Okay, just a quick one. Okay, next, just a little bit. So you have now at V plus is connected with the 400 ohms with the battery. It says the battery is 9 volts and its Zener voltage is Zener reverse breakdown voltage. Remember, Zener has reverse breakdown voltage 6 volt. So then if this voltage, input voltage, you know, even if it is 9 volt, right, since Zener voltage is 6 volts and is in reverse bias condition, right, negative at this side, so this will keep this voltage at V plus at constant 6 volts, right? Voltage across V plus will not go beyond 6 volt because of the Zener diode, right? So that's the thing we have to get. So V plus, because of Zener diode, is VZ, right, is 6 volts, and since again V plus is equal to V minus 6 volt, which we're gonna use, and then after that KCL at V negative, again same thing, right, is now this is at 0 volt, right? So 0 minus V negative divided by 890 ohms plus output, which is it calls V3 minus V negative divided by 1.1 kilo ohm, which is 1100, is equal to 0, right? So this is negative 0 minus negative, because V negative is 6 volt, 890 plus V3 is the V out, which we will be solving for, is equal, and then if you solve that, so you will see the output voltage is, which is the V out, is 13.4 volt if you solve that. So that's the answer. So for this example, if you measure the output voltage here, it's going to be 13.4 volts. Okay, so I'm going to solve the last problem, and all these problems are similar. So again, so here now, instead of just DC volts, you know, you're applying AC volts. It's V1 here, you're applying is 10 cos 10 t volt. It's in, you know, time dependent form. So again, this is the V plus is just the voltage across 5 kilo ohm, right? This 5 kilo ohm. It is from the voltage division, you know, 5 kilo ohm divided by 5 plus 5 times V1. So that's going to be, So 1/2 of V1 is 10 cos 100t volt, which is 5 cos 100t. Right, so V plus is equal to V negative is 5 cos 100t. Right, we're gonna need that later. Okay. Now again, if you just check the first stage, this is the inverting input, inverting op amp, right? Because the input is applied through this this is a DC voltage 1.5 at negative, right? So this is the inverting. So we know, you know the output. So let's call this as VO1. Okay, I'm just gonna call the VO1 because VO1 is just negative 1.5 kilo ohm, which is 1500 divided by 500 ohm. So this resistance divided by that, because this is the formula for inverting amplifier, times and this is going negative 4.5 volt, right? And then the second circuit, you just apply K for the second op amp. You just apply KCL at this node. So for the second op amp, you just apply KCL at V negative. So you have VO1, whatever voltage we found here, right, negative, V negative divided by 5 kilo ohm. So let's put everything in kilo ohms. V out negative, V negative divided by 5 kilo ohm again, right, is equal to 0. But we know all these voltages now, and then you can solve for V out. So VO1 is negative 4.5. We just, V negative is at 5 cos, this is the AC superimposed voltage, 5 kilo, plus V out minus V negative is 5 cos 100t by 5k is equal to 0. And then if you solve for V out from here, is 4.5 plus 10 cos 100t. So that's your final answer. So if you check on the scope with the DC coupled signal, it will be something like that. So you have 4.5 volt DC, right, and it's superimposed by this AC voltage. So it will look something like that. Alright guys, so I hope this sample problems will help you in completing the homework problem, and this I will also post all this as a sample problem, you know, on my courses. Okay guys.